So there's more in my notes on like restriction and the concept of a local inverse. We're going to kind of skip over that for now. Maybe we'll come back to it once we know some calculus. Like it's like as we talk about how do you invert a function and what that means, these things become relevant because just I don't want to write anything. I'll just kind of say it in words. But sine and cosine, they're not one-to-one functions, right? Because if you think about the graph, they fail the horizontal line test, right? Because sine hits like every number between -1 and 1 infinitely many times. You just keep going on and on because it repeats itself, you know? So theoretically, we can only find the inverse to a function which is 1-to-1. So it has to pass the horizontal line test to find the inverse function. So that leaves you with the question, well, what do we mean by inverse sine? Because it's not a 1-to-1 function. How do we find its inverse? And the answer is we restrict sine to just like a little bit of its cycle. So it's just from -π/2 to π/2. Sine goes from -1 up to 1, and it hits every y output just once. So the inverse of sine is actually the inverse of sine restricted to that interval. So that's an example of what's called the local inverse. And so in summary, most functions, if you pick a point, as long as that function is like increasing or decreasing at that point, you can chop the domain down just to focus on that, and then you can find an inverse of the function just with respect to like that restriction. So that's what page 25 is basically about. And on page 26, I give a definition of increasing, strictly increasing, decreasing, and strictly decreasing for a function. I won't write those things out. They are exactly what they sound like, right? The function is increasing. If you think about its graph, it's kind of like going up as you read the graph from left to right. Now, technically speaking, my definitions, if you look at them, if the function was constant, it would be both increasing and decreasing. So constant functions are technically like they're in between. They're like both increasing and decreasing. But a constant function is not strictly. And strictly increasing will forbid the possibility that it like is constant for a little bit. But an increasing function could be like going up and then level off for a little bit and then go up again. Like that's possible. I also define even and odd functions. Do you remember how we define even and odd functions? That I can put. I'll write that out. So f is even if f of minus x is equal to f of x for all x in the domain of f. Now, it looks like I just introduced yet another symbol. So this is shorthand for all. So that's even. F is odd if f of minus x is equal to minus f of x for all x in the domain of f. So you have odd functions, you have even functions. Generally speaking, functions are neither even nor odd. You know, here's a few quick examples. Oh, hey. All right. Here is, you can get rid of the thing I gave you before. These are the ones we are currently on page 26. So actually this is the in-class example. I have f of x is equal to 2 to the x minus 1. Excuse me. Words. So this is in-class example 1.4.25. So here we have f of x equal x to the 2n minus 1, and we have g of x equal to x to the 2n. And h of x equal to 1 plus x. And the question is, determine if the given functions are even, odd, or neither. So how do we check? How do we check if it's even or odd? We try to evaluate the function at minus x and see what happens. Right? So let's work it out. F of minus x is what? Minus x parentheses to the 2n minus 1. So minus x is really minus 1 times x, right? So by the laws of exponents, we've got minus 1 to the 2n minus 1 times x to the 2n minus 1. What is minus 1 to an odd power? See, 2n minus 1 is odd. We're thinking of n as being like a whole number here, right? A natural number. So like minus 1 cubed, or minus 1. Now minus 1 times minus 1 times minus 1. Think about it. 3 minuses. It'd be negative, right? So this is just minus. So it's literally just minus x to the 2n minus 1, which of course is minus f of x. What's that show us? That shows us that a odd power function, right? This is an odd power function because it's x to an odd power, right? Is in fact an odd function. So guess what? An even power function, what do you think is going to happen? What's minus 1 to an even power? Well, it's plus. Like minus 1 squared, minus 1 to the 4th, minus 1 to the 6th, plus. So this is just plus 1, and we just get x to the 2n. We get g of x, right? So even power function's even. All right. How about this last one? What's h of minus x? Well, 1 minus x. And that right there, that's not equal, it's not equal to h of x. It's also not equal to minus h of x, right? So this one, it's not equal to plus or minus h of x, right? So this one is it's neither odd nor even. But like identifying whether a function's even or odd, it's one of the basic things we can do to kind of understand what kind of function we're dealing with. So it's a helpful categorization.
How did you cancel negative and the g of it?
Because minus 1 to an even power is 1.
I got you.
Uh-huh.
Right.
I mean, you could do it like this. Minus 1 to the 2n is equal to minus 1 to the 2 to the n, which is equal to 1 to the n, which is equal to 1. Because it basically all falls back to the fact that minus 1 squared is 1. Now, moving forward here, fun fact, f of x is 1/2 f of x plus f of minus x plus 1/2 f of x minus f of minus x. Now, I'm assuming here that x and minus x are both in the domain of f, right? So this is just like a kind of sneaky trick, all right, that I mentioned at the bottom of page 26, actually in the notes. But this is interesting when you apply it to the exponential. So let's see how that goes. E to the x is 1/2 e to the x plus e to the minus x plus 1/2 e to the x minus e to the minus x. Now, the significance of the formula above is that this right here is an even function, and this right here is an odd function. Because if you put minus x in place of x, you get back the same thing again, and you get the same thing with a minus for the second one. It's even easier to see for this formula, right? If you think about replacing x with minus x for these terms, what happens is just, if you guys look up here for a second, these just flip over. If you switch x with minus x, you get like minus a minus x, which gives me e to the x, and this becomes e to the minus x. If I put in minus x over here, I get e to the minus x, and then I get minus e to the x, so I have to factor a minus out. So this is, now these are not just, I don't think you guys have seen this before, but this, by definition, is what's called hyperbolic cosine, or cosh of x. And this right here is called hyperbolic sine of x. Hyperbolic cosine, hyperbolic sine. Now, they're called hyperbolic sine and cosine because they're very similar to sine and cosine, but they're a little bit different. All right, so like first thing, in class example 1.4.27, show that cosh squared x minus sinh squared x is equal to 1. So this is pretty much just like an algebra problem, right? So I'll start us out. We got 1/2 e to the x plus e to the minus x. I got to take that. I square it. And then I subtract 1/2 e to the x minus e to the minus x, quantity squared. I'm hoping that all simplifies to 1, right? Let's see here. So you get like a quarter for both of them, right? It's because a half squared is a quarter. So I'll pull the fourth out. E to the x, so I guess I'll write it out, e to the x. I'm just expanding what the problem is that's in front of us here. And how do the laws of exponents work for us here? What's like e to the x times e to the minus x? See, e to the x times e to the minus x times e to the x is what? It's 1. Because it's e to the minus x plus x, which is e to the 0, which is 1. In other words, e to the minus x is 1 over e to the x, right? Just to remind you. So like, okay, so like distribute, what happens? What do you got? So we have e to the 2x plus 1 plus 2, so plus 2, plus e to the minus 2x minus 1/4 e to the 2x minus 2 plus e to the minus 2x. So what's going on here is the algebraically, like, I've got this with this, right? And this with this. Both of those give me 1. Those come together to give me this 2. Similarly, over here, I have this, and I have that product. Those both multiply to give me 1. Actually, minus 1, because there's a minus. And that gives me this minus 2 here. I also have e to the x times e to the x. That gives me e to the 2x. E to the minus x times e to the minus x gives me e to the minus 2x. And likewise over here. So what happens is the exponentials cancel, right? See that? These guys cancel out. And you're left with a half minus a half, or 2/4 plus 2/4, which is 1. So this all simplifies to 1. So see, hyperbolic sine and cosine, they're like sine and cosine, right? But a little bit different, right? Instead of cosine, because we have cosine squared plus sine squared is 1, right? Remember from trigonometry? But we have cos squared minus sin squared is 1. So do you guys know what the graphs of the exponential looks like? I'll remind you. So just some walks down memory lane here. The exponential basically looks like this, right? It passes through 1, right? What's the minus the exponential look like? Kind of like the same thing, but well, I could do it on the same plot with a different color, I suppose. Here's y equals e to the minus x, right? So what does the graph of cosh and sinh look like? See, cosh is e to the x plus e to the minus x divided by 2, right? So basically, you just add those two graphs and divide by 2. So cosh looks like this. The domain of the hyperbolic cosine is all reals. What's the range? What's that? 1. Okay. I mean, I agree that this point right here is 1. Very good. Cosh of 0 is 1. But what other y values does it hit? Everything up, right? So 1 to infinity. But that is a very... 1 is the mission. 1 is the critical. That's the smallest it can be, right? So if you have a hyperbolic cosine, you have this inequality. Hyperbolic cosine is larger than or equal to 1. It's a useful thing to know when you're dealing with a problem with hyperbolic cosine. Hyperbolic sine, on the other hand, it looks like this. So I don't think you guys have seen hyperbolic sine and cosine in your previous class, right? Probably not. I probably won't teach them in my pre-calculus either, unless I'm just convinced that the class has been a very good class or something. I don't know, but I think you should see there would actually be completely reasonable things to talk about because they're just adding together examples that you do cover in pre-calculus, right? Exponential and e to the minus x. These are functions we talk about in pre-calculus, right? And all hyperbolic sine and cosine are just adding or subtracting those things. And they actually have very interesting properties. So it's one of the examples we like to have in calculus because it has very nice calculus. This makes a good example for us. to study calculus. All right. On page 27, I remind you how we can create new graphs from old. Do you guys remember? If you add a number to the function, it shifts the graph up. If you subtract, it shifts it down. If you take the argument of the function and you replace x with like x minus c, it shifts the graph to the right. If you add c, it shifts it to the left. You can also stretch it and compress it, all those things. So that's what theorem 1.4.28 is about, just reminding you all that stuff. And in class example 1.429, I'm just going to skip it. Okay. Now, so at this point we have reached story time, all right? So pages 28 through, let's see here, I don't know, 38 basically is a catalog of elementary functions, all right? So you guys can look along with me. So first of all, we can talk about power functions. What's a power function? Power function is something of the form f of x equals x to the a. That's a power function. The first in-class example that we did today was a power function. We had even power and odd power. Now this one, 1 plus x, that's not a power function, right? Because it's not of the form x to the power. That's a power function. Now, if you have the power is like a fraction, that can give you a root function, right? Like x to the 1 over n is the nth root of x, right? Or a negative power give you a reciprocal function, right? X to the minus 1 is 1 over x. That's the reciprocal function. Polynomial functions is what? It's sums of power functions, sums of integer, whole number power functions, right? But you guys know what a polynomial is, right? Like something of the form constant plus constant times x plus constant times x squared and so forth up into a highest power. We'll do more examples of those today. So in this little table, I remind you, that's what the graph of a constant polynomial, a linear polynomial, quadratic polynomial, right? Cubic, them's your basic examples. Turn the page here. We can talk about rational functions, right? Rational functions have a formula that's formed by the quotient of one polynomial and another. Now those are more troublesome to graph because you've got three interesting things going on. You have vertical asymptotes, you have zeros, but you also have holes in the graph, right? A hole in the graph is when you have a factor in the numerator and the denominator and they like cancel out. So it's a place where the function's not defined, but anyway. So there's a typical example in graph. Let's see here. In class example 1.52. What is the domain of f of x equals x to the p where p is a real number? What's the domain of a polynomial? What two features of the graph of a rational function coincide with points which are not in the domain of the rational function? Okay. So, I'll let you guys read the question again, see if you can tell me the answer. So think about this. A vertical asymptote is something that we use to describe a rational function, right? But it's not in the domain of the function. Because it's a place where you have division by 0, right? And your class may or may not have talked about holes in the graph. I know sometimes they don't get discussed here. So let me just give you an example, because I think that I may be talking about something you didn't see in your previous course. It depends. So here's an example. If we have f of x equal to 3x plus 1, 3 times x plus 1, over like x squared minus 1. This is a rational function, right? And it has a vertical asymptote, and it also has a hole in the graph. Let me show you why. So how do you factor x squared minus 1? Difference of squares, right? That's x minus 1 times x plus 1. So what's going on here is f of minus 1 and f of 1 not defined, right? Because they both involve division by 0. However, they're not the same kind of thing, right? Because if you think about it, we could simplify the formula, right? We could just say that that's equal to what? Well, not 0, but how about 3 over x minus 1 for x not equal to minus 1, right? So what's going on here is we have a vertical asymptote at 1. All right, x equals to 1 is a vertical asymptote for this. And it has a hole in the graph at minus 1. So this is just kind of a rough sketch, but something like this is the graph of this thing. But at minus 1, technically speaking, there's a hole. Where is that hole? This hole is actually at minus 1, comma 3 over minus 2, actually. I know that from plugging it into here. So, like if I wanted to if I was just to graph y equals 3 over x minus 1, it would be the same picture, just fill in the hole. That's all. So holes in the graph are kind of silly. They just like move one point. You can always put a hole in a graph by changing the formula ever so slightly. It's very silly. Like, for example, if my function was like this, right? And I wanted to put a hole right here. All I do is take the formula I was given and multiply by x minus 1 over x minus 1. That expression is 1 everywhere except for 1 where it's just not defined. So like, this is the kind of subtle thing we have to deal with if we're going to be careful about domains. Yeah? When you simplify an algebraic formula, you could be changing the natural domain of it. All right. Anyway, let me try not to major in the minors here today. Let's go on. So the answer to the in-class example 1.5.2 was the two features of a graph that coincide with points that are not in the domain of the rational function were holes in the graph and vertical asymptotes. Those are the two features that they're not in the domain of the rational function, and yet they kind of are not, they describe what the graph of the rational function looks like, you know. The two features were vertical asymptotes and holes in the graph. And the answer to what's the domain of f of x equals x to the p, the answer there is it's complicated. It depends. If p is positive, then the domain is like, well, it depends. Certainly it always includes positive x, but like what's the domain of x to the 1/2 power? And what if we have f of x equals x to the 1/2? What is x to the 1/2? Well, that's square root of x, right? What's the domain of that? domain is 0, 0 to infinity, right? So if that p is a even fraction, we have to throw out negative numbers if we want to keep it real. So, but on the other hand, if p is like a whole number, you know, like 1, 2, 3, 4, whatever, certainly the domain of x to the p is the whole reals. If p is a negative number, like if p is like -2, what's the domain of x to the, what's the domain of this one? What's the domain of that function? What do I have to avoid? Cannot equal to 1? 1 is okay. F of 1 is just 1 over 1 squared. What's the graph of this thing look like? This is the... it cannot equal 0, right? This is the... If you look at the graph, I like to call this the volcano function, you know? So there's a tremendous variety of different shapes in y equals x to the p, depending on what p is. Sometimes the domain is all real numbers. Sometimes the domain just eliminates 0. Sometimes the domain has to eliminate all negative numbers. It just depends on what p is. So that's a kind of nasty question in that in-class example. So example 1.53, I give a rational function with a couple holes in the graph. Sometimes the holes in the graph can coincide with where there's a 0. Like a 0 could be, like the graph could cross the x-axis where there's a hole. That could happen. Those kind of look different. The bottom line, though, is to understand whether the rational function is positive or negative, we pretty much need to analyze where the numerator and where the denominator of the rational function can be 0. Those are where everything interesting happens, right? Because the sign of a rational function can change from positive to negative at 3 things. It can change at a 0, it can change at a vertical asymptote. It's going to be vertical asymptote. And it can also change at a hole, potentially. It doesn't have to, but it can. Next up is algebraic functions. Algebraic functions are pretty much functions whose formula is defined by a finite number of algebra steps. And there's a lot of weird stuff that can happen with algebraic functions. The absolute value function is an algebraic function. All right, because the absolute value function is the square root of x squared, right? So that's an algebraic function. And what's the graph of that look like? It's a v, right? So algebraic functions, unlike polynomial functions, can have like jagged cuts in their graph. And they can even have jumps. Like graphs for algebraic functions have all kinds of crazy stuff in them in general. They're really, it's a rich class of examples that's really annoying. The one in this in-class example, 1.5.4, I say find an algebraic formula for that. I'm running a little bit behind, though. I'm going to skip over that. If you want to find it, I'll give you a bonus point. Okay? Any in-class example that I skip, you can work out and give it to me for a bonus point. That should be a rule we have. All right. Next up, I talk about trigonometric functions. I will remind you there's sine, there's cosine, there's tangent, right? They're related to right triangle trigonometry. You can talk about polar coordinates, you can talk about standard angles, all that stuff, right? Okay. I say in-class example 1.55, find the standard angles of 1, 1, and -1, -1, right? So I will leave that as a bonus question for you guys. That's not a hard bonus question, is it? I'm tempted to do it, but I'm not going to do it. I'll leave it to you. All right. I will tell you the answer of one of them, just to make sure we understand each other. Standard angle of like the 0.11 would be pi over 4. So the standard angle, remember, is the angle measured counterclockwise off the positive x-axis, right? For sine and cosine, we have cosine squared plus sine squared equals to 1. In class example 1.5.6, find the identities for the reciprocal trig functions by dividing by cosine and sine squared. Now that one I'll do. In class example 1.56. Okay, so we've got cosine squared plus sine squared theta equals to 1. And so that identity is like immediately known to be true if you define sine and cosine using the unit circle, right? At least that's what I did this week in trigonometry. So like, there's almost nothing to prove. It's essentially from the definition of sine and cosine, in some books at least. Okay, so divide by cosine squared, what do you get? We get cosine squared theta over cosine squared theta plus sine squared theta over sine squared theta equals 1 over sine squared theta. So cosine squared over cosine squared is 1, right? And this can be rewritten as sine, that was a cosine, sorry. Sine theta over cosine theta quantity squared, right? 1 over sine theta quantity squared. What is sine over cosine? Well, sine over cosine is tangent, right? And 1 over sine is... Oh, I'm an idiot. I divided by cosine squared on the left-hand side, and then I divided by sine squared on the right-hand side. Well, that's interesting math. Dummy. Me, not you. So that's supposed to be cosine. What's 1 over cosine? It is secant. Secant, right? So this is the identity 1 plus tangent squared is equal to secant squared theta. So if you know the sine cosine Pythagorean identity, you can derive corresponding identities for secant and tangent. What happens if you divide by sine squared? And I'm saying this one. We get cosine theta over sine theta squared plus 1 is equal to 1 over sine theta squared, right? Which is to say, this is what? Cosine over sine is called cotangent, and 1 over sine is called cosecant. So this gives us cotangent squared theta plus 1 equals to cosecant squared theta. Now, I was overjoyed when I first saw this because then I realized, oh, I don't have to memorize the identities for secant, tangent, and cotangent, right? As long as I remember sine and cosine and this little trick, I can always derive it in a pinch, you know? And next up, I talk about the inverse trig functions. I'll let you look at that. We'll talk about those more when we do their calculus, okay? And then next I talk about exponential functions, all right? I've mostly been talking about the exponential function, right? Base e. The e is in honor of Euler. But generically speaking, you have an exponential function has the form, you know, f of x equals a to the x, right? The a doesn't have to be equal to e. It's still called an exponential function. So in an exponential function, the variable is in the exponent, right? And so it's funny. With that terminology, you'd think that if we had this, right, that should be called a base function, right? Because the variable's in the base, but we call it a power function. I don't know. It's just it's kind of funny. The terminology is not exactly. Anyway, I'm just not telling you anything interesting. All right. We also have logarithms, right? Logarithms are the natural enemy of the exponential. Remind you about that. Page 36, I have all your favorite properties of the log and the exponential, how they work, laws of exponents. I will remind you of these things as they come up in class, all right? I just wanted to put them all together here so we have a reference, all right? And hey, look, hyperbolic sine, cosine, and oh, there's also hyperbolic tangent, which is sinh over cosh, right? So, you know, cosh squared minus sinh squared is 1. You could take that identity and divide it by cosh squared, and that would show you that 1 minus tangent squared is equal to hyperbolic secant squared. Like hyperbolic secant is 1 over cosh. Like everything you know about trigonometry, there's a corresponding like hyperbolic version. Yeah, we'll talk about that as it comes up. There's also inverse hyperbolic trig functions, and they're especially interesting because as you see on page 38 here, it turns out that the inverse hyperbolic trig functions are actually natural logs of algebraic functions in disguise. So we could work through one of these identities here, if you guys would like. But I think I should go on because our time is limited today. I'm trying to remember when we go till what, 45?
Yes.
Yeah. Let me not. I'll leave this example. This is actually. If you just want to come to my office hours someday, I can show you how to work these out. But I think it's a good algebra exercise, but it's not especially like mission critical to us, the derivation. All right, algebra. So let's talk about algebra. These things I will write out. I think the main thing, guys, is basically just factoring. Plain old factoring. That's the major skill that you need to have down, you know, in terms of like polynomials, and also just distributive law. Go for it. So a polynomial is something of this form, right? So here, the numbers an, a1 through a0 are, what are they called? They're the coefficients, right? Coefficients of P. And if a sub n is not equal to 0, then the degree of P of x is equal to n, right? So the degree of a polynomial describes the largest power which appears in it in a non-trivial sense, right? So there's sort of two major categories of doing things with polynomials. The one is solving polynomial equations, right? And the other is manipulating polynomial expressions. These are related but different, all right? So like factoring a polynomial is a way to change the expression of the polynomial in such a way that it's more useful. And that's related to solving the polynomial equation, but it's not the same. Let me show you an example. So polynomial equation, what is that? It's just basically P of x, where P is a polynomial, equal to 0. So you're looking for all the x which you can plug in and get back 0. Now factoring a polynomial, that's doesn't have to be, that's not giving you numbers which solve an equation, right? It's just factoring. But they're related, right? So like in class example, so I ask us to solve x cubed minus 2x squared minus 5x plus 6 equal to 0, right? Now that's a very scary question, right? But I also have given us a hint. All right, and the hint is, hey, by the way, you can factor this polynomial as x minus 1 times x plus 2 times x minus 3. Now that is a very, very generous hint, right? So why does that help us? Why does factoring a polynomial help us solve a polynomial equation? So, because if I call this thing star, right? Star can be rewritten as x minus 1 times x plus 2 times x minus 3 equals to 0, right? And then we get to use a property of real numbers, right? Which is that if a product of real numbers is 0, it must be that one of the things forming the product is itself 0. Like I cannot have a product of real numbers be 0 unless one of those numbers is 0. So that means there really only are 3 choices here. Either this could be 0, or that could be 0, or that could be 0. So how can we make those 0? We can make, x minus 1 equal to 0, or we could have x plus 2 equal to 0, or we could have x minus 3 equal to 0. Now, at this point, we have worked our way back to the kind of problems I was solving for Math 101 this morning. One equation and one unknown. And so those, we just get x equals to 1, x equals to minus 2, and x equals to 3. Now it's important to notice here, that the solutions have a different sign, right, than the factored form, right? Factoring a polynomial is something we do to a polynomial expression. Solving a polynomial equation is related but different. So the solutions here are 1, minus 2, and 3. But notice that the factors are x minus 1, x plus 2, and x minus 3. And you see why there's a difference of sign, right? Because in order to get x minus 1 equal to 0, we must put x equal to 1. Right? So all I said while you're gone is basically, this is a polynomial, its degree is like the largest non-trivial term that appears, and we can use factoring to solve polynomial equations.
I got
Do you guys know about polynomial long division? You've heard of it before? Yeah. So here's the theorem. Actually, you know what? Let me not write the theorem. That actually, I could write the theorem, but it's not particularly helpful. Let me do the example. All right, so if I want to calculate x to the 4th plus 3x cubed plus x squared plus 2x plus 6, and I want to divide x squared minus x cubed minus 3 into that. Oh, what a horrible question. All right. So I can achieve that kind of thing using polynomial long division. Here's how. All right, so I go, I go, all right, in order to get x cubed up to x to the fourth, I got to multiply by x. So I put an x here. X times this gives me x to the fourth minus 3x. Now, I'm going to write the 3x over here, because that's where that is. All right? Then I subtract. The x to the fourth cancels. I've got a 3x cubed plus x squared. Minus gives me 5 plus 6, because minus a minus gives me plus. All right, so next I need to get 3x cubed from my x cubed. So I plus 3, right? X plus 3. That gives me 3x cubed. And 3 times minus 3 is minus 9, so minus 9 over here. And I subtract again. The 3x cubes cancel. I've got myself an x to the fifth plus 5x. Looks like plus 15. And that is the end of the road, because at this point, the remainder has a smaller degree than the dividing polynomial. So that's it. That's it. So this is the remainder. And what this calculation shows you is that this is actually equal to x plus 3 plus x squared plus 5x plus 15 divided by x cubed minus 3. Let's see here. Now, there's something called the remainder theorem. Let p of x be a polynomial. Then p of x equals x minus c times f of x plus the remainder r, and r is equal to p of c. I'll work another example of the long division here. So we have, I'm going to say x squared plus 2x divided by x cubed plus 3x squared plus 2x plus 7. All right, let's calculate that. No, that's not what I want. I'm sorry. No, I'm my apologies. I want to say I'm going to divide x cubed plus 3x squared plus 2x plus 7 by x plus 1. All right. So just to give you, just give you one more example of these polynomial long divisions. All right. So to get x cubed, I have to put x squared. Thanks. And so I got x cubed plus x, right? subtract 3x squared plus x plus 7. So then what's next? 3x, very good.
Wait, why would you only get the single x under 2x if you're multiplying 1 times x squared?
Oh, that's a good question. You wouldn't. So I should have what? I should have,
You should have x squared.
yeah. And then that gives me what? 2x squared plus 2x. Thank you. Whew. All right, then what? So try again. I mean, you were right for my wrong step, but to get the 2x, yeah, plus 2x. Right, so 7, and 7 has a smaller degree than the dividing polynomial, therefore this guy is the remainder. So what this shows is that x cubed plus 3x squared plus 2x plus 7 is actually equal to x plus 1 times x squared plus 2x plus 7. Now, so the claim of the remainder theorem, just to give you an, just to try to get you to understand what's going on here, this is p of x, right? And this is x minus c, right? With what? C equals 2. If it's x plus 1 is x minus c, what does that make c equal to? Got to match the pattern here. C would be not 1, right, but minus 1, right, if I want to match the minus 1. So this 7 allegedly should be p of minus 1 if we believe the remainder theorem. Is it true? What happens when you plug minus 1 into p? Minus 1 cubed, which is minus 1, remember? Minus 1 squared is 1. So I get minus 1 plus 3 minus 2 plus 7. What's that? So 10 minus 3, 7, yeah. So another way to look at this is you could basically factor out an x minus c in this way if you just add p of c over here. Now, what happens when r is equal to 0? Then what we're looking at is something more interesting, right? When r is equal to 0, that means we could factor out x minus c from the polynomial, right? That's actually what the factor theorem says, essentially. The factor theorem. And so the factor theorem is really more what I tend to use. This remainder theorem is sort of just a waypoint to what we're really interested in, which is the factor theorem. Here's the factor theorem. P of x is equal to x minus c times f of x if and only if p of c is equal to 0. So this is the correspondence. Every factor in the polynomial corresponds to a 0 for the polynomial, and vice versa. So if you have information about where the polynomial is 0, that allows you to factor it, and vice versa. Right? So my next example, I give us, of course, but the other thing is we could use long division to accomplish the factoring, actually.